Greetings, this is Professor Roman. Let's continue the lectures in linear algebra. I want to talk today about the spectral mapping theorem, something we've already talked about, but I do want to elaborate on it somewhat. First, I should mention that the term spectral mapping theorem does not seem to be very common in linear algebra. I've looked through my library and I've scarcely found mention of that term. That doesn't mean that the content of the theorem is not present in the books. I'm not about to page through each book and try to find it. The content should be there somewhere, but the term spectral mapping theorem tends to be used in functional analysis much more than in linear algebra. Just as a partial review, if we have a vector space V over a base field F and a linear operator tau on V, and if P of x is a polynomial over the base field, then P of tau is a linear operator. This we've known for some time. The theorem that describes the eigenvalues and eigenvectors of P of tau is sometimes referred to as the spectral mapping theorem. And to understand what's going on, we'll do some exploring. If we start with an eigenvalue lambda and an eigenvector v, that means tau v equals lambda v, then for any non-negative integer k, it's easy to show by induction, for example, that tau to the k v is lambda k v. And because of the linearity properties, this will extend to polynomials in tau. P of tau v is equal to P of lambda v. And so if lambda v is an eigenpair for tau, then P of lambda and the same vector v is an eigenpair for P of tau. And from this it follows that if we take the spectrum of tau, the F spectrum, apply P to each eigenvalue, we will get eigenvalues for P of tau. So this is an inclusion. P of the spectrum of tau is contained in the spectrum of P of tau. And similarly, any eigenvector for tau with respect to lambda is an eigenvector of P of tau with respect to P of lambda. The question now arises, what about the reverse inclusions? Well, as to the eigenvalue situation, if you think about it for a little bit, we might suspect that there could be a problem. As a simple example, if we take a real matrix A and it has a non-real complex eigenvalue, say even lambda equals I, then A squared will have eigenvalue lambda squared, which is -1. And so the non-real eigenvalue has dropped down into the real field for A squared. Therefore, the real spectra of A squared could very well be strictly larger than the real spectrum of A. They should be singular. And here are some examples. Here's a 3 by 3 matrix A and its square. The characteristic polynomials of these matrices are, for A, the factors like this. For A squared, factors thusly. So the complex spectra of these two matrices, for A we have 1 and plus and minus I, and for A squared we have 1 and -1. So the real spectra, we have the spectrum of A is 1, the real spectrum, and the real spectrum of A squared is 1 and -1. So we've had this drop down here, and the real spectrum of A is strictly contained in the real spectrum of A squared. as to eigenvectors, the complex, here's a small complex matrix. Its spectrum contains only the 0 eigenvalue. It's diagonal, 0's on the main diagonal. And the eigenspace is one-dimensional. But A squared is the 0 matrix. Its eigenspace is all of C squared. So that's clearly a strict inclusion as well. So the reverse inclusions in both cases are not going to hold in general. For the eigenvalue case, it seems that perhaps the problem might be that the real field is not algebraically closed. Just a guess at this point. If the real field was algebraically closed, this dropping down business wouldn't make any difference. For example, x squared plus 1, its roots are plus and minus I. They drop down into the real field, but they're still complex numbers, so the complex spectra hasn't changed any. But this example shows that for eigenspaces, for eigenvectors, it doesn't matter. This is all done in the complex field, and we still have a strict inclusion. So we take a closer look at the situation for eigenvalues with under algebraically closed base fields. I'll call that K an algebraically closed base field. Suppose that lambda v is an eigenpair for p of tau. We want to show, that means that p of tau minus lambda v is 0 for some non-zero vector v. Have that. Since k is algebraically closed, we can factor this polynomial p of x minus lambda and say it factors into linear factors like this. Since v isn't 0, this product applied to v is 0, but one of the vectors in the following list, so we start with just v itself, that's non-zero. We don't know about applying tau minus Rn to v, or this product to v, and so on. But when we get to the full polynomial p of x minus lambda, we do get 0 when we apply it to v. Somewhere there's a last vector that's non-zero. Could be v itself, might be the one just before the last one, we don't know. But if we call it w, it's of the form tau minus rk plus 1 through tau minus rn. V is non-zero, but when we apply tau minus rk to w, we get 0. So r sub k is an eigenvalue of tau with eigenvector w. We needed to go through this because we needed to make sure w was non-zero in order to be an eigenvector. So rk is in the k spectrum of tau, but it's a root of this polynomial, which means that p of rk, which is equal to lambda, because if you put rk in here for x, you get 0. P of rk is equal to lambda, but this is in p of the spectrum of tau. So the reverse inclusion, we started with lambda being an eigenvalue for p of tau. We see that it's also in the set p of the spectrum of tau. So the reverse inclusion holds and we have equality. So what we now know is that the inclusion 4.9 in general is not an equality, but it can be upgraded to an equality if the base field is algebraically closed. At the same time, 410 cannot be improved to an equality even if the base field is algebraically closed, as the previous example showed. But there is still something we can do with 410, the eigenvector inclusion. If we have two different eigenvalues of tau, it's possible that when we apply p to them, we get the same value. That means both of these eigenspaces is contained in this eigenspace. It's the use of 410 twice. So the direct sum of these two, these are essentially disjoint, so the direct sum of these two is contained in this eigenspace. And more generally, if we have an eigenvalue of tau, then this would apply to all the eigenvectors, all the eigenvalues that have the same p of x value as lambda. So we get an inclusion that looks like this. The direct sum of all the eigenspaces, E sub mu, where p of mu is equal to p of lambda, is contained in the eigenspace of p of tau associated with p of lambda. I don't know if you can see this in the camera. It's kind of small. I hate using these really small subscripts, but I don't do it too often. So this is the best we're going to be able to do for eigenspaces. But there's something else we can do for eigenvalues, for spectra, because we know that equality holds in 4.9 for an algebraically closed field, so we can pass from whatever the base field is f to its algebraic closure. We discussed that briefly, that concept before. So the f spectrum of p of tau is equal to the f bar spectrum of p of tau intersected with f. Remember that the spectrum, the eigenvalues of an operator, are the roots of the characteristic polynomial. So what we're saying here is that we take the characteristic polynomial p of tau over f bar. It factors into linear factors. We get a bunch of roots. We're taking those roots that are in f. Those will be the eigenvalues in the f spectrum. They're still eigenvalues. They're still roots of the characteristic polynomial, but they're roots that belong to the base field, f. Now we can use the spectral mapping theorem. We have an algebraically closed field. 4.9 tells us that this is equal to this. So the f spectrum of p of tau is in fact p of the f bar spectrum of tau intersected with the base field f. And so this is a summary theorem for what we will call the spectral mapping theorem. The reason I wanted to go over this again with a little more detail is because something happens that's good when the operator is diagonalizable. It has to do with this. If you look at this, if tau is diagonalizable, the direct sum of all the eigenspaces is all of v. So as we scan through the eigenvalues and we collect all these inclusions, on the left side, the sum is going to be v. On the right side, it's going to be in v. Everything's in v. This is going to be equal to v, and it's going to turn out that this will become an equality. And that we're going to discuss next. If a linear operator tau is diagonalizable, and if p of x is a polynomial over the base field f, then the operator p of tau is also diagonalizable. To see this, one can proceed by taking a matrix point of view. It's not too difficult. Or by using the spectral mapping theorem, which I think in some ways is easier. It shows you more clearly what's going on with the eigenvectors. So that's the approach we will take. Suppose that tau has spectrum lambda 1 through lambda m. Then the spectral mapping theorem tells us that P of the spectrum of tau is contained in the spectrum of P of tau. Recall that this is an equality when the base field is algebraically closed, but we're not assuming that now. And for each eigenvalue lambda, the direct sum of the eigenspaces for tau associated with the eigenvalues that have the same p-value as lambda is contained in this eigenspace of p of tau. But the diagonalizability of tau implies that V is the sum of all of tau's eigenspaces, direct sum, in fact. And so when we take the sum of these direct sums, we're getting then the sum of all the eigenspaces for tau. It's contained in the sum on this side, but the sum on the left here is all of V, so the sum on the right is also all of V. So V is the sum of all these eigenspaces for P of tau. Now, this is not necessarily a direct sum because different lambdas may produce the same P of lambda values. So some of these terms may be identical. And so we have to deal with that if we want a direct sum. And all we have to do is assume, by re-indexing if necessary, that the distinct values among these subscripts here, these p-values, that they are p of lambda 1 through p of lambda r, where r is less than or equal to m. So just pick out distinct values from this list here and re-index. So now we can write a direct sum decomposition of V where the eigenspaces range from p of lambda 1 to p of lambda r. Well, that shows that p of tau is diagonalizable. The spectrum of p of tau is this list of p-values, which is p of this list. These are distinct, but once you apply p, again, they may not be distinct anymore. That's p of the spectrum of tau. So we have equality in this case. So if we have an algebraically closed base field, we'll have equality. If tau is diagonalizable, we'll have equality. As for the eigenspaces, if we again take direct sum of these direct sums, that's the sum over all the eigenspaces. So we get V, but each of these is contained in the corresponding eigenspace for P of tau, and this now adds up to V as well, so we have an equality here. And since this summand is contained in this summand and down the line, each of these must actually be equal. So we were able to improve this inclusion to an equality, which we could not do before. There is a more elegant way to view this, and I guess it's arguable that maybe I should have done it this way in the first place. And that is to define an equivalence relation on the spectrum of tau by saying that two eigenvalues for tau are equivalent if and only if their p-values are the same. And then this equation says that this eigenspace, the p of tau eigenspace for p of lambda I, is the direct sum of the eigenspaces of tau ranging over the equivalence class that contains lambda I. So we are summing on equivalence classes here. We now have what I am calling, and I don't think anybody else would, or does, maybe they would, but they don't, the spectral mapping theorem for diagonalizable operators. V is a vector space over base field. We have our polynomial diagonalizable operator. And if this is its spectral resolution, where rho sub k is, as usual, projection onto the eigenspace associated with lambda k along the sum of the other eigenspaces, and by reindexing, if necessary, we get the distinct p-values on the spectrum. Then p of tau is diagonalizable. It has this spectral resolution. And let's see. Yes, that's fine. Just occurred to me I may have said something wrong, but no, it's okay. So the spectral resolution of p of tau looks like this, where the pi sub i's, pi sub k, is projection onto this eigenspace along the sum of the other eigenspaces for p of tau. I can't use rows because they're projections onto eigenspaces of tau. I need projections onto eigenspaces of p of tau. So the spectrum, p of the spectrum of tau is equal to the spectrum p of tau, and we have this sum here over the equivalence classes. Well, now we can establish the final two correspondences in our matchup here between normal matrices and complex numbers. We've seen that the self-adjoint matrices correspond to the real numbers through their eigenvalues. Unitary matrices correspond to numbers on the complex unit circle. We're going to now see that positive definite matrices, which we first encountered as Graham matrices for inner products, correspond to positive real numbers, and positive semi-definite matrices correspond to non-negative real numbers. So we'll start with the definitions here. Let tau be a self-adjoint operator with quadratic form q sub tau. Tau is positive definite if q sub tau is positive definite, and that means that q sub tau is a real function. Its codomain is, or its image is real, and q tau of v is positive for all non-zero vectors v. Tau is positive semi-definite if q tau is positive semi-definite, which means that, again, q tau is real, but now q tau of v is non-negative for all vectors v. A couple of comments about this definition. First, there is some variation in the use of these terms. For example, some authors refer to an operator simply as positive when it's positive semi-definite. Not too crazy about that, but it's done. Also, for complex operators, the condition of self-adjointness in the definition isn't really necessary because it follows from the positivity conditions, either one. And actually, it follows from the fact that the quadratic form is real. That's all it takes. Because then if you take a vector v and you compute tau v, which is the quadratic form for v applied to v, this is the sesquilinearity. It's the conjugate symmetry of the inner product. We can remove the conjugate because this is real. Move the tau to the other side. And now if you look at the first and last, holding for all vectors little v, in the complex case, but not in the real case, this implies that tau star equals tau. In the real case, we do need the requirement that tau be self-adjoint, but in the complex case, it follows from these two positivity conditions. So I had two choices. I could have given you two separate definitions, but since it doesn't do any real harm to include the self-adjointness condition, even when it's not needed in the complex case, I did it that way, so I only had to give you a single definition. May not be best mathematical practice, really. One doesn't like to include conditions in a definition that aren't necessary, but I guess I broke my own rule this time and did it that way. I'm going to leave it for you to show that a positive definite operator is invertible, and now we can complete this correspondence. A normal linear operator tau on a finite dimensional inner product space is positive semi-definite if and only if all of its complex eigenvalues are non-negative. So that is the correspondence here, the last one. And similarly, positive definite if all of its complex eigenvalues are positive. As to the proof, if tau is positive semi-definite, and if we have an eigenpair for tau, then positive semi-definiteness is this condition. This is the definition of the quadratic form. Tau v is lambda v. V is non-zero because it's an eigenvector, and so this requires that lambda be non-negative. So that's one direction here. All the eigenvalues are non-negative. Conversely, suppose that all the eigenvalues are non-negative, then tau is self-adjoint because the eigenvalues are real. So that's an earlier correspondence. And all of its complex eigenvalues are in fact non-negative, which we're assuming. So that's why they're real. So we can then take an eigenbasis for the pair v tau. And if these are the eigenpairs corresponding to the eigenbasis, so lambda is the eigenvalue corresponding to ui, then any vector v is a linear combination of the basis vectors. And so q tau of v, which is by definition this quantity, simplifies to this sum, which is non-negative because the lambda i's are non-negative. And so tau is positive semi-definite. That's the proof for one. The proof for two is analogous, and I'll let you do that if you're interested. Positive operators, and by that I mean either positive definite or positive semi-definite, have square roots, and they have unique positive square roots. And to see that, let's take a look at again at the spectral mapping theorem for diagonalizable operators, which we talked about earlier, but I just want to restate it for reference purposes. So here is the statement of that theorem. For diagonalizable operators, this is an equality. P of the spectrum of tau is the spectrum of P of tau, and we have an equality for the eigenspaces here. This is the direct sum over the appropriate equivalence class. Using this notation and this theorem, if the polynomial P of x mapping the spectrum of tau to the base field is injective, then we don't, if you look back at this theorem, remember we picked out the distinct values among the p-values of the eigenvalues, and we got a possibly shorter list. Well, if p is injective, we don't get a shorter list. We get the same list. So that means that where are we here? R equals m, and this is the injectivity. So this condition, this formula for the eigenspace just becomes this. The eigenspace of tau associated with lambda I is the same as the eigenspace of p of tau associated with p of lambda I. This direct sum, in other words, reduces to a single term. So the spectral resolution of tau looks like this, and the spectral resolution of p of tau then looks like this. Notice that the projections are the same because the eigenspaces are the same. Okay, that's the real point here. So it follows from this that if we have any family C of diagonalizable linear operators, and if the polynomial P of x is injective whenever it's restricted to the spectrum of any of those operators, then if we take an operator sigma in this class, there's at most one operator tau that fits this equation, because sigma, which we are given, uniquely determines the p of lambdas, but that uniquely determines the lambdas because of the injectivity of P of x on the spectrum. So sigma determines this list of numbers, which uniquely determines the eigenvalues of tau, which in turn uniquely determines tau, because they're diagonalizable. But this operator, we can take P inverse of the lambdas, because again, P is injective. This operator does fit this equation. So in other words, this equation has a unique solution within the family C. Okay. And we could call it P inverse of sigma. The most common use of this theorem is in the case where C is the family of positive semi-definite or positive definite operators, and P of x is x squared. In this case, all the eigenvalues of the members of the class C are either non-negative or positive. P of x is injective, and so for any sigma, this is given by its spectral resolution, there's a unique operator, tau, which is the square root of sigma, given by this spectral resolution. This is called the positive semi-definite square root of sigma. And a similar argument will apply to the positive definite operators. Here's one use for square roots. If tau is positive definite, the square root of tau is self-adjoint. It's still normal, because it's a polynomial in tau. And its eigenvalues are real, because this is the real, this positive square root. These are positive square roots here. So square root of tau is self-adjoint, and we can write then square root of tau star, which is the same as the square root of tau, times the square root of tau is equal to tau. Conversely, if tau has this form, sigma star sigma, for some invertible operator, then tau will be positive definite. It's certainly self-adjoint. If you take the adjoint here, you get tau back again. But also, tau v is sigma star sigma v, which is sigma v, which is positive. And so tau is positive definite if and only if it has this form, sigma star sigma. This is the analog of the fact that a complex number z is positive if and only if it has the form w bar w for some non-zero complex number w. And similar conclusions hold for the positive semi-definite case. And so that's the statement here of this theorem.